So we're going to start chapter 13. At this point in pre-calculus, we kind of start circling back and overlapping topics from Algebra 2. So this chapter 13 is going to be about polynomials, topic we've already discussed. We'll do some extensions or extend some ideas of what you would have already talked about in Algebra 2 and do a second pass over some skills and try to develop some mastery on things that you would have done in Algebra 2. But this is kind of the next several chapters are rehashing and extending and developing some mastery on ideas from the Algebra 2 class. So this next several chapters should feel familiar. So we'll do polynomials and rational functions and exponential and logarithmic functions. So all things we should have hit in our Algebra 2 class last year. If not, and we're going to see it for the first time now. If you already did, then it's just time to pick up some mastery and extend a couple of ideas that we had introduced last year that we're going to explore a little deeper this year. Okay? So a little bit of vocab for us to start. So let's say we have some polynomial function. We'll call this function y equals f of x. So the first thing we're going to talk about are some key features on the graphs of polynomials. So the first one would be the zeros, which is kind of the same thing as an x-intercept. So if I look at my graph, I'd see like 3 zeros on my graph. Everybody okay with that idea? The next key feature I want to talk about are extrema. And there's actually 4 types of extrema. There's absolute or global. You can use those two terms interchangeably. Maximums, absolute minimums, local maximum, and local minimum. Now, any polynomial graph may have 1, 2, 3, 4, none of these, which they don't all have to occur on every polynomial function. Does anybody remember the difference between an absolute extrema and a local extrema? Okay, so for example, an absolute maximum is a point whose y-coordinate is greater than or equal to all the other y-coordinates in the function. Does this graph have an absolute maximum? What did you say?
No, because there's an arrow.
Yeah, no, because we have an arrow pointing up, right? Any point you pick, I can find a y-coordinate or a point with a y-coordinate higher than that one because the arrow is extending up forever. By that same notion, does it have a global or an absolute minimum? No. Okay? So a local maximum or minimum means that I can find an open interval where there is a highest or lowest point on that open interval. So for example, if I look from like here to here, there's a local maximum. you see any other local maximum? No. How about local minimum?
I like the dip.
Yeah,
2 and 3.
exactly. Everybody feel okay there? Okay. And the third type of key feature we want to talk about for a polynomial is the end behavior. Okay. So what the end behavior is doing is it's describing what the arrows on the graph are doing. So if I look at this graph, how many arrows are on my graph?
2.
2, right? So we'll have an end behavior to describe each of these 2 arrows. Everybody feel good about that? We'll talk about how we're going to write that end behavior in a minute. If I look at this arrow is on the left-hand side, and it's pointing down, right? And this arrow over here is on the right side, and this one points up. Everybody okay there? So the way that we're going to describe our end behavior is using something called a limit notation. So the way that we're going to write that So we're going to write it like this. The boxes that I've drawn there are the pieces that you're going to fill in depending on what the graph looks like. But every end behavior you're going to write limit as x approaches whatever the function name is, f of x or g of x or an equation, and then equals something. Okay?
How's it going?
Meeting for a while, or I don't know.
Yeah, thank you. Okay. So, when I talk about the side, we're doing this limit here. So the left side, we're going to represent as negative infinity. Because as that arrow goes to the left, the x-coordinate on all those points is tending towards negative infinity. Equals, points down is talking about the y-coordinate. As we move points along this curve, since it's going down forever, the y-coordinate is tending towards negative infinity also. Everybody okay with that? So if I look at my other end behavior, since this is talking about the right side, if I follow along on this graph and I look at the x-coordinate, if I'm moving to the right, the x-coordinate is tending towards positive infinity. And because the arrow's pointing up, the y-coordinate is tending towards positive infinity. So that's how I'd write the end behavior here for this graph. Is everybody okay there? So again, the side, what we're talking about is what's happening to the x. the point is what's happening to the y. Does everybody feel okay about the limit notation? Again, you're communicating something that's really obvious, it's just presenting the notation for you guys, and I'm trying to like decode it enough to where it's simple to write. Everybody's okay? So this feels like a test question, right? Here's a graph, give me the, the extrema and the zeros and the behaviors and, right? The other way that we could ask this same question is we could give you a function and ask you to do the same thing, like find the zeros and the extrema and the, actually I think I want to, don't write this one down. I think I'm going to steal a specific example from the notes because I don't want this thing to get too funky on me. They don't have one. Okay, that's probably fine then. I'll just do that. And we'll do this. There we go. Okay. And let's say we asked for the zeros, the extrema, and the end behavior. Yeah.
For this question, would you factor out x?
No. So the actual question that we're asking here, some of these questions are quite difficult, right? To just go from an equation. And in fact, finding the extrema is something, to do that is beyond the scope of even what you would be expected to be able to do in this kind of a math class. Unless you have some help. What kind of help are we going to be using?
Calculator.
The graphing calculator. Yeah, so if you want to take your graphing calculator out to kind of follow along, we're going to use our graphing calculator to do this kind of a problem. Okay, everybody ready? We're going to start by looking at the graph of this. So to graph an equation, what I'm going to do is I'm going to start by pressing the y equals button. And I'm going to input the equation exactly as it looks, say, into y1. So anything else that's in here, I'm going to clear out. And just type in, oops, that's plus. Get rid of that guy. Now, in the previous chapter, we've been graphing things with scatter plots and stuff. So up here where it says plot 1, 2, and 3, I want to make sure all of that is not highlighted anymore. So if you have any of those plots 1, 2, or 3 that are highlighted, that are turned on, just use your arrows to move up and press enter to unhighlight it so you don't end up getting an error because it's trying to graph a scatter plot and maybe you don't have points in there anymore. Okay, everybody got the stuff in and the plots turned off? The next thing that I'm going to do is I'm going to look at the graph of this. The best way to graph this, again, since we've been looking at scatter plots and stuff, who knows what our graphing window looks like right now? So I'm going to press zoom and I'm going to pick option 6 for standard. That just sets the window to go from -10 to +10 on the x's and -10 to +10 on the y. if I can't see everything I needed to from my function, I might go in and manually adjust the window, but this looks pretty good to me. Everybody agree? Okay. So what I'm going to do now is I'm going to use my calculator to locate the zeros, and then the extrema, and then I'm going to have to write the end behavior by hand. But that, from the graph, that's easy to do, right? Once I have the picture, no problem. Everybody ready? Okay. To get the zeros, I'm going to press the second button, and then the trace command up there at the top row. Which command sounds like the one that I want if I'm looking for the zeros?
Zero.
The zero command, of course. Okay, so if I look at the bottom of my screen, my calculator is now going to ask me 3 questions. It's going to ask me for a left bound, a right bound, and a guess. Now the calculator is dumb, so you want to make this as simple as you can possibly for the calculator. To do that, I want to pick my left bound and my right bound so that there's only one 0 in between them. So I'm going to find this 0 first. So I'm just going to move somewhere to the left of it, press enter, and I move somewhere to the right, but I don't want to go too far right because I don't want to go past the next 0. So that looks good. You see the dashed lines? That's the place where my calculator is going to search for zeros. There's only one 0 there for it to find. The third question is a guess. Because there's only one thing for it to look for. Does the guess matter? Nope. You just got to make sure that it's, between the 2 lines. I just press enter wherever it is. So there's my first x-intercept, is the point 0, 0. Does everybody feel okay there? Repeat that process and find the next 2 points. I'll do the same thing while you guys are working, and we'll see if they match. How'd that go for you guys? No problemo? Getting fairly? Yes.
Mine says bang bumped up in the air.
That means that when you picked your left bound and right bound, it didn't cross the x-axis anymore.
Got it. Okay.
So if it says no sign change, it meant that you picked 2 things that were there's no place where it crossed in between. So it's I can't find anything there.
Got it. Okay. I think I did it a slightly too far to the right.
And again, if you look at the bottom here, it'll tell you the coordinate. So you can tell if it's above or below the x-axis by looking at just the sign on the y-coordinate.
Okay.
And that's helpful too, right?
Thank you.
Sure thing. Everybody happy? Next thing we're going to do is hunt for extrema. If I look at my graph, what kind of extrema do I see? I see 1 local minimum and 1 local maximum. Everybody agree? Okay. Let's find the coordinates now of those points. So I'm going to press second and the trace button again. And what commands do you suppose I'm going to be interested in here? Minimum and maximum. So let's find the local minimum first. So I'll pick the minimum command. Now the calculator is going to ask me the same 3 questions. Left bound, right bound, and guess. So I'm going to take my cursor and I'm going to move it somewhere to the left of where I think that local minimum is and press enter. Now for the right bound, I'm just going to move it somewhere to the right of where I think that local minimum is. And as long as there's only 1 minimum in between, my guess doesn't matter. I'll just press enter where I'm at. And there is my answer, so rounded to 2 decimal places. We'll do that, and I'll note that that was a local minimum. Everybody feel okay there? Try to find the local maximum now on your own. So just kind of repeat the same process with the maximum command. I'll do the same thing up here. We'll compare answers here in a moment. Yeah, sorry. I was just double checking that. You're right. And I'll note that that's my local max. How did that go? No problems? All right. The last thing we need to do is write our end behavior. So the calculator won't help me do that other than provide the graph for me to look at, which hugely helps, right? So I'm going to look at this arrow first. Which end of the graph is this? The left end. And which way is the arrow pointing? Up. So we'll write limit as x approaches negative infinity, because it's the left end of f of x, equals positive infinity because the arrow is pointing up. Everybody feel good there? Try writing the other end behavior on your own. I'll write up the correct answer in a moment, but try writing the other end behavior on your own, and then we'll check it against my answer here in just, I don't know, 30 seconds or something, just to have a little bit of practice on doing this. So that's the correct answer. The limit as x approaches positive infinity of f of x is equal to negative infinity, because my right-hand arrow is pointing down. Everybody feel okay on this? This feels like a series of test questions right here. Basically just checking if you can use the calculator and know the vocabulary, right? Feel good? Okay. That was basically section 1. Okay. We're going to shift focus now to talk about finding these zeros algebraically. So we have our calculator. We can use our calculator to find zeros. With technology, we'd like to still be able to do this algebraically by hand. The first thing you probably should have noticed is that there can be multiple zeros for a polynomial, right? So what we want to do is we want to create some like upper bound on how many solutions I should be looking for. So when I start this solving process and say I don't have a calculator, I know that, okay, I can't have more than whatever number of solutions, or zeros, I should say. Is everybody okay? So our first theorem that we'll see this chapter says that a polynomial of degree n will have at most n zeros and at most n minus 1 extrema. So if I have a quadratic, that's a degree 2 polynomial. That means at most that quadratic could have is 2 zeros and 1 extrema. If I have a cubic polynomial, that's degree 3, means it can have at most 3 zeros and 2 extrema. Could it have less than 3 zeros? Yes. Could it have less than 2 extrema? Yes. All this theorem is doing is giving me an upper bound, right? If I have a cubic polynomial, it could have 3 zeros, could have 2 zeros, it could have 1 zero, it could have 0 zeros. So the at most phrase there is doing a lot of lifting for us. Is everybody okay there? Okay. All right. So our basic method that we're going to use to solve or to find these zeros. We're going to factor the polynomial. We're going to set it equal to 0. And then we're going to use the zero product property, I've abbreviated that as ZPP, to solve each of our individual factors. So that's just a basic outline of the procedure we're going to use. What's the hardest part about this procedure? It's going to be the factoring these. So what I'm going to do now is we're going to build together like a flow chart that's going to describe to you how to factor a polynomial in general. I'm going to warn you, this is quite a large diagram. It might need a full sheet of paper depending on how large you write and how neat you are. And it gets quite wide, so you may want to write this like landscape style instead of portrait style. Just like turn your paper on the side. I'm just warning you, you can do what you like. I'm just, you know, there's like the first step and then there's 4 branches. So it's going to get kind of wide. All right. So I'm going to zoom out so I can get an outline of what I'm going to do, and then I'll zoom in on the individual steps here in a second. Is that okay? So it's going to be, if you can't read it right now, that's okay, because I'm going to zoom in and go through, write things in individually. I just need to have enough, see that I have enough space to put in what I'm going to put in. All right. So we have some polynomial. The first thing that we're going to look for is, can I factor off a greatest common factor? Is there like a factor of 2 on every coefficient? Is there multiple powers of x on every term? And I factor some stuff to the front. After I've checked that and factored if it's done the greatest common factor, if there is one, I look at the number of terms. So we're going to have 4 branches from there. You're going to have either 2 terms, 3 terms, 4 terms, or 5 or more. Okay? So that's my next set of branching. I'm pause here while you guys kind of outline. There's a lot of stuff that goes underneath these, so give yourself some room because there's branching that's going to happen underneath each of these, 2-term, 3-term, 4-term pieces. Okay, we ready? I'm going to zoom into the 2-term and we're just going to work down this branch now. So the first question we ask, if there's 2 terms, we want to know, is it a difference of 2 squares? That's what DOTS stands for, difference of 2 squares. And I wrote the factoring pattern below. If it's yes, we do that factoring, and then we have to check each of those 2 factors, my A minus B and my A plus B, down the 2-term branch again. Everybody's okay there? If there's not a difference of 2 squares, then we ask ourselves, is there a sum of 2 cubes or difference of 2 cubes? And I'll write the factoring patterns for those here below. Oops. If I put the right one in the right spot. So SOTC stands for sum of 2 cubes. DOTC stands for difference of 2 cubes. And I wrote the factoring patterns for each of those below. So if that factor you're looking at is a sum or difference of 2 cubes, then you factor it. And then you have to take that binomial factor, either the A plus B or the A minus B that you generate, and check that down the 2-term branch. If it wasn't a sum or difference of 2 cubes, then we stop. There's nothing more we can do. Is everybody so far okay? Sure. Can I go back up to the 3-term branch now? We've completed our 2-term branch of this tree. We're going to go to the 3-term now. So the first thing we're going to ask ourselves, is our polynomial in the quadratic form? So the quadratic form is like ax to the 2n plus bx to the n plus c. So something like x squared plus x to the first plus 1, that's in the quadratic form. But so is something like x to the 6th plus x to the 3rd plus 1. Is everybody okay with that? So it's not limited to just quadratics. It can be anything where the degree of the polynomial is twice the degree of the linear term or the middle term and then a constant. Everybody's okay? So if the answer is no, well, there's nothing more we can do there. We would stop. If the answer is yes, then we ask ourselves, is the leading coefficient equal to 1? That's what the A is there, right? We're talking about the A from up here. So we're talking about the leading coefficient. Why am I checking that? You remember when you factored last year in Algebra 2, it was way easier to factor a quadratic when the leading coefficient is 1 than it was when it wasn't, right? So if the leading coefficient is 1, we can do we check to see if we can do the short factoring, find two numbers that multiply to give us C, add to give us B, right? Maybe I'll write that in. If I can do that short factoring, then I have to check each of the resulting factors down the 2-term branch. If I can't factor it, then I just have to stop. There's nothing more for us to do right now. If my answer was no, if the leading coefficient wasn't 1, then we have to check to see if we can do the long factoring. So to do that long factoring, we have to find the two numbers that multiply to give us A times C and add to give us B. And we use those two numbers to create a new 4-term polynomial that we factor by grouping. Just kind of outline that process there for you guys. You should remember that. That usually gives Algebra 2 students pull some hair on those ones because it's a little bit trickier. So if we can do that, just like before, then we have to check each factor down the two-term branch. And if it can't do that factoring, then we have to stop. There's nothing more for us to do there. Everybody still doing okay? That completes the three-term branch. Now we'll go to the four-term branch. Everybody ready? Are we still writing? Okay, yeah, that's why I asked. You can tell me in 1 second if you're still writing, no big deal. Got lots of time. It's the last idea I need to do for today, so we're just gonna finish this diagram and then do some practice using it. Okay, so we have lots of time left to do that. So I'm not in a rush, I just also don't want you to sit there twiddling your thumbs waiting for me to, while we're sitting here doing nothing. We good? Okay. All right. Now down the four-term branch. We'd want to check, can I use factor by grouping? If I can't, we stop. There's nothing more for us to do right now. If it's yes, then I have to check each factor down the two-term branch. That completes the four-term branch. So either you can group it or you can't. And then our last step is 5+ terms. We don't have anything to do for that yet. Now, I'm going to tell you right now, this is not complete. So this is what you would have done last year in Algebra 2. All these places where there's a stop, we're going to end up extending this factoring diagram by the end of this chapter. So we're going to build this thing out and give us more options that we can try to continue factoring things. Everybody good so far? Okay. So we're gonna crank through a couple examples using this to find some zeros, and that'll be it for today. Sound good? I know that was a lot of writing there, so I appreciate you guys hanging in with me. This time I am going to use the examples from the book so that I can make sure I have something that has reasonable, oh gosh dang it, have reasonable answers to it. Okay. If I look at my factoring diagram, what's the first thing we look for?
Terms.
Greatest common factor. Do I have one for this polynomial?
X.
I have an x. So when I factor that x out, what is left?
X squared minus 6x minus 8.
Yep. And we have a little bit of a boo-boo here. I have a typo on the notes. That should be plus 8. So make that change for yourselves. It should be plus 8. After we've looked for our greatest common factor, we look at the number of terms. How many terms do I have left? 3 terms. If I go down the 3-term branch, what's the first thing I check?
Is it in quadratic form?
Is it in quadratic form? Well, definitely it is, right? It's a straight up quadratic. That doesn't get any more quadratic form than that. After that, I look
Is the
to see,
leading coefficient 1?
is the leading coefficient 1?
Yes.
Yes, okay. And then I should do
The short factor.
the short factoring. So I'm going to look for 2 numbers that multiply to give me positive 8 and add to give me negative 6.
Negative 4, negative 2.
Negative 4 and negative 2. Okay. After I've done that, it tells me to check each one of these down the 2-term branch, right? This is a degree 1. Can it be a difference of 2 squares?
No.
Can it be a difference of, or sum or difference of 2 cubes? No. Same thing here, right? So we're done. Everybody feel okay? So that's the factoring complete. To find the zeros, I then set this equal to 0. And then I apply the zero product property, which allows me, or what the zero product property says, if I have some stuff and I multiply that stuff together and it equals 0, means that one of those, at least one of those things that I multiplied together was 0, right? So that allows me to take each factor and set it equal to 0, and then I can solve them individually. X equals 0, I love that, it's done for me already, yay! And then we'll add 4 to both sides for this guy. Another 0 found, and add 2 to both sides for this one. Another 0 found. This had 3 zeros. What was the max number of zeros we could have? 3. Have we found them all?
Yep.
I certainly think so. Does everybody feel good? Okay. You ready to do another example? Okay. I think we'll probably do 2 more and then call her quits for today. I think that sounds pretty good. The directions here are just a tad different. It says find the zeros and the multiplicity of the zeros for the function yada yada yada. When you see the term multiplicity, do you remember what this means? It's just the number of times the solution occurs. So up here, 0 occurred 1 time, has a multiplicity of 1. 4 occurred 1 time, has a multiplicity of 1. 2 occurred 1 time, it has a multiplicity of 1. Something makes me feel in this question, one of the solutions is going to happen more than once. But let's see. Here's my polynomial. First step is
Factor.
greatest common factor. Is there a greatest common factor there?
X.
I can take out an x. Next I look at
Terms.
number of terms. How many?
3.
3. And then I check,
Is in quadratic form.
okay, is it?
Yes.
Okay, then I look for,
Is A equal to 1?
Leading coefficient of 1, is it?
Yes.
Okay, then I do.
Short factor.
Great. Two things that multiply to give me 9 and add to give me 6.
3 and 3.
3 and 3. Okay. Oh. And then my last step would be to check these down the two-term branch. They're both linear. There's nothing more I can do with those. Is everybody okay how that I hand wave through that? We'll do an example in a second where it's important that I go back through because there's additional stuff I could do. All right, we'll set it equal to 0 now. Apply the zero product property. X equals 0.
Equals 3, or 1, -3.
That's a multiplicity of 1.
And then -3 is multiplicity of 2.
Yes, because that solution occurred more than once. So I'd say the other solution is x equals -3, and that has a multiplicity of 2. Feel pretty good? Okay. We'll do, say, one more example. Yeah. So we have x to the 6th minus 1. First thing I check for is
Factoring.
greatest common factor. Is there one?
No.
No. Okay. Thank you.
Yeah, thank you.
Then I look at the
Number of terms.
number of terms. How many do I have?
2.
2. So down the two-term branch we go. What's the first thing down the two-term branch?
Is there a difference of 2 squares?
Difference of 2 squares. What did you got? What do you guys see? Okay, write that as something squared minus something squared.
Yeah.
Okay, I agree. Let's start with the easy one.
-1.
1
Or
is
just 1.
1 squared, right? X to the 6th is
X to the 3rd.
x to the 3rd squared. Good, because I know that when I have an exponent of an exponent, what do?
Multiply them.
Multiply the exponents, okay? So anytime I have like an even degree here, and there's 2 terms, I'm thinking probably a difference of 2 squares, even if this number is kind of kooky. Everybody's good? Okay, so that allows me to write this as that. Pretty good?
Yeah.
Okay, after I've done my difference of 2 squares and factoring, it says to
Check it back on the 2-term.
check this down the 2-term path. So I got to check each one of them. X cubed minus 1, is that a difference of 2 squares? Cannot be because it's an odd degree. Is it a sum or difference of 2 cubes?
Yes.
Yes. So here I have like that. So my A is X and my B is 1. Is everybody okay there? And we'll check this one now. Also not a difference of 2 squares, but it is a sum of 2 cubes, right? I can do the same kind of trick there. So plug it in. And then I need to check these 2 guys down my 2-term branch. They're both linear though, so I know they're going to be fine. They don't do nothing. Is everybody good to how I've gotten to here? Okay. Factoring is now done. We checked as far as we could go. Notice that we had to cycle through that 2-term branch a couple of times to pick up all the factoring that could happen. That's okay. That's why everything loops back to the 2-term branch. We can apply our zero product property now. Start with the easy ones. Any questions on how I did those? Lord help me, right? How am I gonna solve x squared plus x plus 1?
Three terms.
Well, okay, you wanna try to short factor that. What are two numbers that multiply to give me 1 and add to give me 1?
Don't work.
Doesn't work. How do I solve a quadratic if I can't factor it?
Quadratic equation.
The quadratic formula, yes. Do I expect, is that a reasonable expectation that we have this memorized at this stage?
Yes.
I think it is. That says for the quadratic equation, ax squared plus bx plus c equal to 0, x equals negative b plus or minus square root b squared minus 4ac all over 2a. You don't have that memorized? I would say the expectation B is you are going to be a freshman in college. Your professor would expect that that is something you have committed to memory. Okay, so on this one, A is 1, B is 1, and C is 1. Everybody good how I filled that into the formula? What do you notice?
So they're an imaginary number in the square root.
Yeah, the negative square root of a negative creates an imaginary number. How do I represent that? With an I, right? The I is outside the square root. Everybody okay there? Okay. We'll do the same thing over here. So A is 1, B is negative 1, C is 1. Yeah, so those are technically two separate solutions, right? But what are the zeros for this? What are the zeros for this function? Just 1 and negative 1. Why don't these count? Yeah, because they're non-real. That is, does not represent a place where the graph can cross the x-axis. My only zeros are at 1 and negative 1. Does everybody feel okay there? Pro tip. The quadratic resulting from the sum or difference of two cubes always have imaginary solutions. So if you followed the factoring diagram in the order that I've given it to you, you'll always encounter the sum or difference of two cubes quadratic where it's going to give you an imaginary solution. What do you guys think? Does this feel okay?
Yeah.
Fairly familiar to things you did last year? This should have been something that we were approaching mastery on. At this point, I'm going to assign 1 through 15. Use the calculator to find zeros in extrema. At most, how many zeros in extrema could the function have? Don't have to do anything for that, barely just look at it. Describe the end behavior using limits. I would have the calculator give me the graph, so I could do that. Find the zeros algebraically. I guess we don't want to do that one yet. So let's take off for you guys. We'll go to 12 or something there. We should do 15. Let me do 15. I got an example in the one more example to do. I lied about being done with the examples. We'll do one more example. That'll allow me to assign 15 also. Okay. This says that a company wants to create a cardboard box with an open top. The box needs to have a volume of 500 cubic inches and is to be created by cutting squares from each corner of a rectangular piece of cardboard in order to create tabs to fold up. The piece of cardboard is 26 by 20 inches. What size squares should be cut from each corner in order to create the proper volume? Okay, so here's my sheet of cardboard. And I'm going to take a little snippy from each corner. I don't know how much I have to snip yet, so that's going to be a variable. We'll call that x. Since we know those are squares, I'm going to label all those sides x. Everybody feel so far so good with the picture we've drawn? Who remembers how to calculate the volume for like some rectangular solid like that?
Times width.
Great, length times width times height. My problem with that, though, is that there's 3 separate variables in that. I want to reduce that down so that it has 1 variable. Okay? So if I think about my picture, this side here, from there to there, would be like my length. And then like this, from like here to here, would be my width. And then like this would be like my height. Everybody imagine that as we fold this box up. Okay. So one of these is quite easy. My h is just going to be x, right? What is the length going to be? I should give myself some more space. If I look at this side here, how do I represent that side in yellow? How big was it before we cut out our squares? 26.
X.
And then how many squares did I cut out?
2.
2. And how much of the length did I remove?
2x.
2x. So I should write this as?
26 minus 2x.
26 minus 2x. And then how about for the width?
20 minus 2x.
20 minus 2x. Same reasoning. Everybody feel good? What does the volume have to be here? We're told in the problem it has to be 500. Everybody feel good there? Okay. So what I want to do is I want to solve this equation. I'm just going to subtract that 500 over. And now it's calculator time. What am I looking for here? If it's set equal to 0, I'm looking for the zeros for this function. So I'm going to, on my calculator, I'm just going to graph this function. Come back over here. And then use the 0 command. So I'm going to have 26 minus 2x, and then 20 minus 2x, and then x, and then minus 500. Is everybody okay with how I set that up? Now I want to think here for a minute, because I'm betting that I have to make some intelligent choices about my window here. So let's think about what are the biggest and smallest values that x could possibly have. What's the smallest value x could have reasonably?
1.
Well, less than 1. About 0, right? Right? X is a length. The smallest length you can reasonably have of something is 0. What's the biggest value for x that I could have?
Less than or equal to 500.
Nope.
Probably not.
Way smaller than that. Which side is smaller, the 20 or the 26?
20.
The 20. How big could x get before I have some arithmetic cutting that doesn't make sense? 10. What would happen if x is bigger than 10?
Equals 0.
I have to cut off 22 inches of 20. That can't happen, right? The biggest my x could possibly be is 10. Everybody agree with that? Now, the y coordinate, I don't care, because all I'm looking for is where it's crossing the x-axis. Y negative 10 to 10 sounds perfect. All I care about is where it's crossing. I don't need to see the whole thing. There's 2 crosses. So define those. Second trace, 0 command. My left bound I need over here. So that looks like, if I'm looking, that's 1. So I need the x here to be less than 1, or, so I'm going to keep pressing. Notice my cursor's off the screen somewhere. That's fine. So I'm basically just watching for that to go negative. See the y-coordinate go negative? Even though my cursor's off the screen, that's fine. I'm going to press enter. Now for my right bound, I'm just going to keep pressing right until I see this y-coordinate go positive. It's gone positive. That's good enough. Press enter again. So 1.2 is one of my possible values for x. And I need to find this one. So second trace, 0 command. This is fine right here, because till I get to the other side, that's fine, right? So I'll press enter, and then I just keep pressing until I see the y-coordinate go negative again. It's going to be a minute. Still, finally started getting smaller now. It's going to take a minute. And there we go. It went negative. So I'll press enter again, and then enter on my guess. 702 is my other value. What do you guys think? Use the calculator. The algebra here would be El Stinko. We don't want any part of that. Let the calculator do the heavy lifting for me. For those of you that are juniors and have an ACT or something coming up, this is a perfectly reasonable method of attacking any solving problem that you don't know how to solve on an ACT. Just graph both sides of the equation and find the intersection, or move it all onto one side and look for the x-intercepts. That'll work. Even if you don't know how to do the algebra, the calculator can do it. You'll have the calculator the whole time. Take advantage. Very helpful. Now I'm super done. Sorry for I forgot to do this one. Alright.